Okay, in this lecture, what we're going to do is we're actually going to graph polynomials. We're going to do it by hand. We're not going to use a graphing calculator. We're going to do that on Monday. So the graphs that we're going to get are not going to be totally accurate, but close enough. Now, it's going to be better than the sketches that we've done. A couple things we need to know first is what we call a turning point. So when I have these polynomial functions, as you have already seen, we can get some weird looking shapes out of there. And what we'll see is that they create little local minimums and maximums that we call turning points. And we're going to find the values of that on a graphing calculator on Monday. But for now, we just need to know those are the turning points. And they are also called local min and maximum. So if I needed to find the value of a local maximum, this would be a local maximum. Notice that on this little hump on the graph right here, that it is the top. That would be a maximum, but it's called a local max. And this part down here would be a local min. These points here are the zeros. Okay? So I think maybe in your homework assignment, it may say find the value of the local max or min, and you'll be looking at a graph that's already given to you. You're not going to be able to do that very well if you graph it by hand because you're not going to have enough points to do it real accurately. One thing about these turning points is that the most I could ever have is equal to the degree of the polynomial minus 1. So if I had, say, an x to the 6th, a degree 6 polynomial, I could have a maximum of 5 turning points. Okay, and of course, an x to the 6th could just look like a parabola if it was a real simple x to the 6th, or it could look like something like this, and we could see we would have a turning point, a turning point, a turning point, a turning point, and a turning point. So it's a 6th degree. I would expect that it could have at most 5. This one has 1, 2, 3, 4, 5. So sure enough, but it's not going to have any more than that. So here is the relationship between the degree of the polynomial and the maximum number of turning points it could have. That would be the maximum number of local minimum and maximums. Okay, so let's go on to now graphing these polynomials by hand. And what we're going to do is we're not going to get perfect graphs. The first thing you have to do is you have to find the zeros of the polynomial. And you may have to factor it. This one is already factored, and I have these factors 1, 6 times x plus 3 times x minus 2 squared. Now, when I look at this, I know that this factor right here will create a repeating point because it has a square, an even power there. So that's going to be a touch point. The other one is a first power. It's going to pass through there. So let's go ahead and plot the zeros. So if I have a factor of x plus 3, the 0 would be a negative 3, 0. Let's go ahead and plot it. And if I have a factor of x minus 2 squared, I'm going to have the 0 at 2, 0, but it's going to be a repeating 0. So I'm going to go ahead and put that on there. Now then, what we are going to do is we want to plot one point on the outside of the zeros. So out here somewhere, and we're going to plot the point directly between the two zeros. Now, the book will say plot a couple points in here, and they'll pick some right here on the grid lines, but I'm just going to say go halfway between and pick it. Let's just have a constant way of doing it. Yeah, it may give us a fraction we have to plot, but we have these calculators that are scientific and graphing calculators that we could plug numbers in and get the values pretty easily. So what I would do is let's talk about the points I'm going to use. Since here's my last 0 at a negative 3, I'm going to go take a point to the left of that, so I'm going to plug an x value in of a negative 4. Then I'm going to go between my two zeros. If I had 3 zeros, I would have to do 2 points in between there. 1 point in between each 0. Since I only have 2 zeros here, that limits how much I have to do, so it's easier for me. But so if I, in between, it's 1, 2, 3, 4, 5, so I'm going to have to go 2.5 from the zeros, would bring me right in here at a negative 0.5, so I'm going to plot a negative 0.5. And then I got to pick a value that is greater than my last zero out here to the right. And so I'm 1, 2, it looks like I'll pick a point out here. I'll pick the 3 for x. So I plug those values in for x, and I'm going to use my scientific or graphing calculators, plug a negative 4, so I put a negative 4, 1/6, times in parentheses a negative 4 plus 3, times in parentheses a negative 4 minus 2, cursor 2, or caret 2 for the square. So, and that's what I get. So be careful with your parentheses and your exponents when you put them in your calculators. And these are the values that I get out. So I'm going to go ahead and plot them. I'm going to say if I have an x value of a negative 4, I get a y value of a negative 6. 1, 2, 3, 4, 5, 6. Now sometimes these may fall off of your graph. Then just put a point way down here, and that's good enough, right? We're just getting a general shape. So if I have a negative 0.5, I get 2.6. And at 3, I get 1. So it looks like that my graph is going to be something that looks like this. Let's switch to a different color. And that would be my graph. Now, your book says they don't suggest you plot points on the outside of your zeros. They just say use end behavior. I would prefer to see you try to plot it because I think you get a better shape than if you're just saying, oh, it's going to go down, the right is going to go up. So just check it with your end behavior. Does it make sense for what you have? Well, I have a first power and a second power, so I have an x cubed polynomial. The leading coefficient is positive, so I would expect that polynomial to look like that. And sure enough, that's the kind that I got when I graphed it. So I'm using my end behavior to kind of double check, and that's what it would look like. So anyway, that's how we plot these polynomials.